Well, thank you, Debbie, for that very nice introduction. And it's a pleasure to be here to celebrate this occasion with you. I'm very, very happy to be asked to give this talk because we've worked so closely with NERSC over the years. So first of all, I just want to go back to a quote from Bill McCurdy, who was the Associate Lab Director for Computing Sciences when NERSC first moved to Berkeley from Livermore. And he said, if NERSC does not enable a major scientific discovery every few years, we're not doing our job. And as you'll hear in my talk today and the other talks following, this bold challenge has been spectacularly met. And I want to, in particular, talk about some of the contributions that NERSC has made to discoveries in physics and cosmology, in particular, discovery of dark energy, study of cosmic microwave background, radiation, neutrino oscillations, and the Higgs boson. And there is much more, but in 30 minutes, I can't begin to cover it all. But we're engaged in a really exciting intellectual journey. I call it connecting the quantum and the cosmic, where we have these two theories. The theory, oops, that's okay, a little musical accompaniment. Ta-da! We have a standard model of cosmology, what we call our lambda CDM model, which describes the history of the universe. And we have the standard model of particle physics, which describes the smallest building blocks of the universe, the quarks, the leptons, neutrinos, the force carriers between them, the Higgs boson. And what's really exciting is that these two models come together. And if we really understand the building blocks of the universe, then we should be able to go back to the dawn of time, right after the Big Bang, when all particles and their antiparticles are equally created, and understand then how they interact and roll the movie forward and see how did the universe evolve. And when we try to do that, we test both models, the model of cosmology and particle physics, and we find some very interesting things. In particular, early on, there is a period of immense exponential acceleration from inflation, which we believe had to have happened, although we can't look back that far, but because our universe has a flat geometry and is isotropic, something must have happened that caused it to expand very rapidly. And as the universe then expands and cools, and it's a hot, dense plasma, at some point, it cools enough that you can form atoms, and photons are released from the plasma, and that's the cosmic microwave background radiation. This earliest light, it is like the baby pictures of the universe. And then as the universe expands and cools, it begins to decelerate because gravity as a long-range force is attractive. And it was thought that this would just continue to decelerate, maybe coast to a stop, maybe go back into a big crunch. But as I'll talk about in a minute, I need some IT support, I think. Oh, there we go. It's very slow to respond here. There we go. As it was discovered in the late 90s, in fact, the universe is not slowing down, but it's accelerating again. And we don't know if this is related to the early period of inflation or if it's a phenomenon, but we don't really understand it. So we've gone from a situation where particle physicists, we thought we knew all the building blocks and really understood the universe in detail, to a situation where, in fact, we don't understand most of the universe because there's also, in fact, most of the matter is not baryonic matter composed of the quarks and leptons, but is dark matter that is gravitationally interactive but does not emit light. So in fact, about 95% of the universe is composed now of dark energy and dark matter. A tiny fraction is in normal matter, and that is dominated by neutrinos and stars, because guess what? We've also learned that neutrinos are massive. When I was a grad student, they were massless. And not only that, but there's no antimatter, even though after the Big Bang, there should have been equal amounts of matter and antimatter. So there's so many things we don't understand, and NERSC has played an important role in helping us understand these puzzles. So I'm going to talk about just 4 of them: the dark energy, the cosmic microwave background radiation and inflation, the neutrinos, and the decays. So let's start with NERSC's role in the discovery of energy. So this goes back to the very first days when NERSC just moved to LBL. There was a research group led by Saul Perlmutter called the Supernova Cosmology Project. And Saul stopped by Bill McCurdy's office one evening and said, "Hey, we'd really like to use your computers because they're attempting to measure something called the deceleration parameter of the universe using type 1a supernovae as a standard candle. So if you can catch a supernovae early enough and plot the light curve and measure its peak luminosity, you can then use that supernova to, by measuring the peak luminosity is a standard candle, you know its distance, you measure its redshift, you plot the two, and it can tell you the expansion rate of the universe versus time. And the expectation was that it would be slowing down. And this required quite a bit of computation. So there was an early LDRD that was supported by both the physics division and by NERSC to hire an astronomer with expertise in computing, Nugent. And then they used the M-Curie system, which Sudeep mentioned earlier, to both for the supernova discovery, where they had to coordinate telescopes all over the world to take an image and then 3 weeks later take another image, and this delivered supernovae on demand. So because supernovae are going off in galaxies all over, and if you can coordinate according to the phase of the moon and take these images and subtract them digitally, you can discover supernovae on demand, and then you can schedule follow-up and have those resources all lined up. So you can trace out the light curve, get a spectrum to confirm that it's a type 1 and so on. So this required computing just to carry out this program. And then on top of that, they only discovered 42 supernovae, but yet they were able to make a 5 sigma discovery of dark energy because they used every statistical method in the book running on M-Curie, and also Peter Nugent simulated 10,000 supernovae explosions so they could understand the biases of their analysis. And what they found was that the supernovae, in fact, if you plot the expansion versus time, it's, as you go back in time, it's less, which means that as you go forward in time, the expansion is speeding up. And so contrary to expectation, the universe is not decelerating, but accelerating, a totally unexpected result. And so this is the return of Einstein's cosmological constant. Einstein had introduced this to create the universe to be static instead of expanding, called it his greatest blunder. And now it's come back with a vengeance. Instead of a matter-dominated and flat universe where they expected it to be around here, they found that we're somewhere in this ellipse where the cosmological constant is non-zero, and we are not a matter-dominated universe at all. So this was a huge surprise. Another group found the same thing, and Saul shared the Nobel Prize with Schmidt and Rees in 2011. This is the group there, Peter Nugent there in the background. Very exciting event for the lab and for Saul. And since then, we've continued to play a leading role in trying to understand what is dark energy. It's dominating the energy budget of the universe, but what the heck is it? So there have been many generations of experiments, both studying supernovae, but also using a new technique instead of a standard candle, using a so-called standard ruler in the distribution of galaxies. And so we started doing that with the BOSS experiment, which I worked on, and its successor, eBOSS. And now we're operating the Dark Energy Spectroscopic Survey, DESI, which has a focal plane with 5,000 robotically positioned fibers that can take 5,000 spectra every 15 minutes we have tens of millions of galaxy redshifts that allows us to plot out the large-scale structure of the universe and measure dark energy with the standard candle. And the motto is that Stephen Bailey has come up with, who runs all this, is the red shifts before breakfast. So we take the data, we send it to Perlmutter, gets processed, we get the red shifts, we feed that back, and can plan the next night's observations. And Desi has recently come up with a tentative evidence that dark energy may not be a cosmological constant. It may be changing in time. We'll need more data. And luckily, they're getting more data in real time as we speak. And so the mystery of dark energy, we may be able to say more about that in the next few years. Now let me turn to another mystery, which is the acceleration from inflation. So I mentioned that this is like the baby picture of the universe. The first light emitted as the universe has cooled and expanded. And the structure in this light can tell us a lot about the early universe. And the cosmic microwave background radiation was discovered in 1964, actually by accident. Penzias and Wilson, they had a mysterious noise in their radio telescope. And after they eliminated every possible systematic and source, including bird poop that might have collected on their telescope, they concluded it was the cosmic microwave background, confirming the Big Bang Theory, and they won the 1978 Nobel Prize in Physics. Of course, they didn't use NERSC for that. That was before NERSC. But then our own George Smoot was a PI on the NASA's COBE satellite, which then detected the small fluctuations or anisotropies in the CMB, which is a key prediction of inflation. And he shared the Nobel Prize in 2006 for that. So this established CMB. It's a very interesting field of research, but there's much, much more in the cosmic microwave background. We often call it the gift that keeps on giving, because if you can measure the temperature of the CMB as a function of scale, and the power spectrum is that red curve there, that can tell you whether the universe is flat or curved, how much of it is ordinary baryonic matter, are there light relic particles out there? And then you can start looking at the polarization of that light, and both in the E modes and the B modes, and that can tell you more about the universe, like when did the first stars form, where's the massive neutrino, or what we're really on the hunt for now, when did inflation happen? And this little bump that you see down there, labeled R equals 0.1, 0.01, et cetera, that is the bump that we're looking for as would be the so-called smoking gun, that this inflation actually happened. So we need to go way, way down in precision and lower noise, and that's requiring more and more computing. And I like to show this plot that Julian Borel has put together that shows the blue dots show supercomputing power in flops going up with Moore's law, perhaps bending over as Moore's law begins to fail, and the rate of data coming from ground-based CMB experiments basically tracking that. And then we're extrapolating out into the future for what we expect from future experiments. So we really have these huge data sets. We need supercomputers to keep up with that. And that has required CMB scientists to be always on the bleeding edge. And that's where NERSC has really come in to deal with this data deluge. So, for example, in 2000, there was a balloon experiment called Boomerang. It was led out of JPL. The data analysis was performed at NERSC using the same Cray computer that Saul Perlmutter's group used. And Julian Borel wrote a code called MADCAP. And they then you get the blue ellipse there. You can see that the supernova data that I showed earlier and the CMB data are orthogonal. And that tells you that we live somewhere around that red star where we have about 70% dark energy, 30% or 25% dark matter, and only 5% baryonic dark matter. So these results from Boomerang, the first that showed us we live in a very strange world dominated by dark energy and dark matter. And in other words, 95% ignorance. We have a lot that we need to understand. The next set of major results came from the Planck satellite. So we get up above the Earth's atmosphere, you can get a much better picture of the CMB. You don't just have to look through the little windows where the CMB can get through the atmosphere. This was a partnership between the European Space Agency and NASA. And NASA reached out to DOE and said, we'd like to partner with you to take advantage of the computing at NERSC. So this was a pioneering agreement between us and DOE, and the analysis was carried out through 6 generations of NERSC computers with big increases in speed all along the way, enabling this beautiful curve that you can see here, the power spectrum for the temperature anisotropies. Then really we're now getting into an era of precision cosmology. And this was made possible by the LBL team who developed this toast package. They had to constantly evolve it to keep up with the evolving computer platforms. That's kind of a recurring theme in order to get to the 1% uncertainty level. And NASA recognized Julian with the Exceptional Achievement Award in 2016. And the other photo there is showing David Skinner accepting the NASA Group Achievement Award in 2018. So NERSC really played a key role in these beautiful results from Planck, which had taught us so much about the universe. And NERSC continues to host the data from all the major ground and space-based CMB experiments today. And the next thing that we're planning is the what we call CMB S4 or CMB stage 4, which will be a big ground-based CMB experiment. It's really going in, focusing in on that polarization signal, the B modes, so that we can look for that little bump that we have to dig out of all kinds of noise from galactic foregrounds, from the atmosphere, from gravitational lensing of the signal, and dig that out. And so we're bringing together all the CMB groups who are working on different experiments around the world into one team. We'll be producing 1,000 times the data volume of Planck. And we will, LBL was chosen to be the lead lab for CMB-S4 in a significant part because of our history of CMB data analysis at NERSC. And so we had originally planned to site our telescopes at the South Pole and in Chile in the high Atacama Desert. NSF has recently told us that they cannot host new experiments in the South Pole. So we're in the process of re-optimizing the experiment to be based only in Chile. And we're doing lots of simulations, and we're using NERSC quite a bit to come up with a re-optimized design. So next I want to change gears and talk a little bit more about particle physics and talk about NERSC's role in neutrinos. So as I mentioned, neutrinos actually make up a significant fraction of the mass, ordinary matter of the universe. They are not massless as originally believed. And how did we come to know this? Well, there was an early experiment by Ray Davis detecting electron neutrinos from the sun underground in a mine in South Dakota, and he was only measuring about 1/3 of the expected number. And that was a big mystery. So an experiment was designed called the Sudbury Neutrino Observatory in a mine in Canada with heavy water. And LBL played a major role in SNO. And it was designed to try to understand what the missing neutrinos were by being sensitive not just to electron neutrinos through charge current interaction, but also to muon and tau neutrinos through neutral current interactions. LBL, as I said, played a big role. Kevin Lesko led the fabrication of the support structure. The nuclear science division contributed a lot. Craig Tull led the computing at PDSF. And by measuring both the electron neutrinos and separately the muon and tau neutrinos, they determined that in fact, the electron neutrinos, you're only measuring about 1/3 of them because they're oscillating into muon and tau neutrinos. You're losing 2/3 of them. And they were able to detect that. And for this, the PI, Art McDonald, shared the Nobel Prize with Takaaki Fujita, who had another experiment in Japan called Super Kanda in 2015. So this was a major breakthrough and a very well-designed experiment to understand what was really going on. So now we knew neutrinos are oscillating, but there were still some people who said, well, maybe it has something to do with the magnetic fields in the sun, or this is really what's going on. So there was people were trying to then detect this oscillation from neutrinos that were produced in reactors. These are actually anti-electron neutrinos. And so if this is really oscillations due to quantum mechanics, these anti-neutrinos should also oscillate and disappear. So the Camland experiment was led by Stuart Friedman of UC Berkeley and LBL in collaboration with a group in Japan. They set out to test this by putting an underground simulator-based experiment in the Kamioka mine. And there are many, many nuclear reactors in Japan. This is sort of an average weighted distance of about 175 kilometers. And so you can see from the plot that they had a much longer baseline than the earlier experiments, which had not detected any oscillations. And already in the first 6 months of data, they at that time, there was no ESNet, so they wrote it to tape. They flew it on a plane to HPSS, transferred it, and then processed it at PDSF. And the oscillation signal was so large that they detected it immediately. And that same year, they were able to present it at fall conferences. So this was actually another major result that confirmed this hypothesis that neutrinos can oscillate. Now, if there's three neutrinos and they're oscillating into one another, that's going to be governed by a big matrix, mixing matrix. And there's three angles in that. And two of them had been detected, but the third, theta 1,3, the mixing between the eigenstate 1 and eigenstate 3, had not been detected. So the hunt was on for this. And quite a few people thought they were going to be able to measure this. So there were several experiments being built to look for what would be called short baseline neutrino oscillations. So the Diabé experiment was led by Ken Bullock, UC Berkeley professor and LBL faculty scientist, in collaboration with a group in China. They put their experiment near a big nuclear power plant in Diabé, China. And there were many contributions from LBL to both the hardware and the computing, which again was led by Craig Tong. And they analyzed their data at NERSC over Christmas 2011 and made, just a few months later, made the announcement of a large value of 81.3. You can see there the near detector, EH1, EH2, and then the far detector, EH3, where you can see the far detector is, you're seeing a dip, and that's that short baseline oscillation. So this was they scooped everybody else thanks to the NERSC processing all this data over Christmas. And this unexpectedly large value for theta 1,3 also opened the door to be able to measure another parameter of the neutrino mixing matrix, the CP phase. And so that led to the proposal for this large baseline neutrino facility, DUNE, Deep Underground Neutrino Experiment, LBNF DUNE, which is a major facility now being constructed at Fermilab and South Dakota. So when neutrinos are produced at Fermilab, they're shot underground, they arrive in South Dakota, comparing neutrino and anti-neutrino beams and seeing whether or not they're CP violating. LBL is leading the near detector, and Dan Dwyer has developed bubble chamber-like readout. Neutrinos were amazingly, at the near detector, you actually have so many neutrinos that you can readout. And we're also working on other experiments such as mass scale and whether neutrinos are their own amplifier. There are other experiments. So we continue to be very active, and NERSC continues to have its. Okay, so my last topic is going to be the Higgs. I think all of you know that the Higgs has been long predicted in particle physics as the sort of the mysterious particle that gives all the other particles their mass. And so this is the Large Hadron Collider that was one of its main physics goals at CERN, where we participated in the Atlas experiment. And this was announced on July 4th, 2012, that the Higgs-like boson had been discovered. This is NERSC is hosting both Atlas and CMS experiment for many years. And going back to 2000, when they hosted the first Atlas software tutorial, Paulo Calafia has been leading this Athena analysis framework for many years and through many, many generations of computers at NERSC, always adapting. And today, Atlas is the #2 CPU user at NERSC, and NERSC is the #5 resource provider in the Atlas computing grid. And of course, this discovery of the Higgs just the year after the Nobel Prize was awarded to Peter Higgs and Francois Englert for their theory of prediction. And NERSC continues to play a unique role. And we're now looking forward to run 3 at the after run 3, we're going to have the high luminosity upgrade of LHCs. That will be even more challenging to access all these many terabytes of data and do all the simulations. And so we're still relying on NERSC as a major resource. And new users are coming every year to use NERSC to make precision measurements of the Higgs and to look for new physics at the large hadron. So that brings me to the end of my rapid fire survey of some recent developments in particle physics and cosmology. I want to thank NERSC for over 30 years of partnership in discovering the secrets of the universe. To more discoveries in the years to come. I mean, we have many more experiments planned or being built. And there are many topics I did not mention. LZ, dark matter experiment that we lead, is also a major user at NERSC. We're looking for new heavy elements at the 88-inch cyclotron. We're studying the quark-gluon plasma at RIC and then at the electron ion collider at Brookhaven. We're doing advanced accelerator simulations for Bella to try to advance accelerators to new technologies, et cetera, et cetera. So there's just a lot more that I just didn't have time to mention, but thank you very much. And we look forward to continued partnership.